All right, so we are recording. Let me hand it over to Group 5 to share with us your zebrafish spin design.
All right, good morning, everyone. We're Group 5, also named Poseidon, and we're going to be presenting today our zebrafish environmental habitat. I'm Rachel Lucas.
I'm Augusto Munoz. Sorry about that.
I'm Augusta Seal.
I'm Brian Mejia.
I'm Chase Manning.
I'm Heian Wang.
I'm Shanghai.
All right, so I'm going to go over what we're going to be talking about today. We're going to talk about our hedgehog concept. We're going to go through our product overview, so subsystems, how they work, our key design features for our design, and then we're going to go over how much this is going to cost. And then we're going to refresh and go over any other questions you may have, and you can ask us about that, all of that at the end. So our hedgehog concept. We wanted this to be very user accessible. So we designed everything with the operator in mind. It's easy to pick up, it's easy to clean, it's intuitive to operate. It's also very affordable. So very cheap to manufacture and cheap to produce. And I think, and we all think, our design is best for its low assembly time and its low manufacturing time. It's very quick to produce. So what is our product? We have an add-on zebrafish imaging kit, including a laser path map and environmental habitat. So you can see these graphics on the right, a little simplified model of our imaging chamber, sample holder, and laser path design. Essentially, our imaging chamber provides appropriate living conditions for a zebrafish sample. We have a holder that can move the zebrafish sample up and down and keep it comfortable while it's being scanned. And we have an optogenetic simulation laser path design for sample imaging, which we'll use to scan its brain chemistry. And we designed it in a way that it would not take and objectives. We designed for high opacity and for minimal light loss and high imaging quality for the chamber and the sample holder. We designed it to be biocompatible and water resistant. And we also designed it to be easy to clean and aligning with all safety standards. It's also easy to assemble and affordable. So here's a more complex graphic of everything working together on the imaging table. We have the optogenetic laser path up on the upper left-hand corner, and it travels up the left side of the table all the way to the right side to the fish holder and the imaging chamber, which are small and a little bit small to see, but they're linked together at the very end, and everything meets together at a point where you can easily scan the fish and nothing will interfere with the other laser path already present on the table. So a little bit more numbers to get involved. The project area is 1.24 meters squared, which is the area of the entire assembly all put together. The weight of all custom parts is 307.14 newtons. Our prototype cost will amount to, in total, $75.57. And our production run cost with 100 units is $4,678 total. All right, so when designing for our customer, we mapped out all of their needs that they specified they needed. So for instance, our 488 nanometer laser path must not interfere with the already existing 639 laser path. It must be directed along optical paths. The imaging chamber must be at a specific size. All fish-related parts, so the fish holder and the imaging chamber, must be biocompatible and compliant with BSL-1 standards. And the imaging chamber and fish holder are cleanable and easy to clean. We also ensured that our prototype was below the $300 prototype max cost, and we also very much ensured that the production cost was well below $200. And upon taking all these customer needs, we translated them into more specific language and defined units for all of these needs, which you can see here in this graphic. It's a little bit more expanded. For instance, we ensured everything was at specific angles. We ensured the mounting heights were all specifically correlated with each other. Everything was spaced apart enough quickly. And after all of that, we spaced these things into subsystems, which we'll go into a little bit more on the next slide. But we have the optogenetic laser path, which is the 488 nanometer laser. We have the imaging chamber, and we have the fish holder. So again, a little bit more detail on our subsystem. We have the imaging chamber, which is on the far left, and it is composed of the actual chamber itself, which will hold water and will hold the zebrafish while it is being scanned. It also includes the mounts for the zebrafish imaging chamber. We have the fish holder, which is composed of the mount for the fish holder and the actual fish holder itself, both of which the imaging chamber and fish holder are designed to be clear and easily biocompatible as well. And then we have the optogenetic laser path, which you can see on the far right. And that is designed to hit the imaging chamber and hit the fish holder at a specific point so you can easily scan your samples.
Okay, so we have the first subsystem analysis, which is the imaging chamber. So the imaging chamber, based on this exploded view of the assembly, the imaging chamber has 4 imaging chamber mounts, 2 imaging chamber side panels, 1 imaging chamber bottom panel, 1 imaging chamber back panel, and an imaging chamber window. So based on our customers' need statements for the imaging chamber, we make sure those following points. So first of all, we need to make sure the imaging chamber is water resistant. Then we make sure it has high transparency for high imaging quality. Then we make sure we use the biocompatible material, which will not impact the zebrafish sample on the inside the imaging chamber. And then we make sure the dimension of the imaging chamber are perfectly fit into the microscope's working spaces. We make sure it is 76.2 times 38.1 times 76.2 times 76.2 times 38.1 milliliter for the whole dimensions. And for the optical table, we make sure it is 76.2 times 38.1 millimeter, which can make sure the laser beam has enough space to do the scanning and also do the movement. To reduce the scattering effect and to make sure it has the highest transparency, we make sure the imaging optical window is 1 millimeter thick, which is the easy purchased and also easy to fabricate it. And we find a balance between these parameters. And for other imaging chamber panels, we choose the 3 millimeter thick, which can make sure it's also balanced between the transparency and price and also the fabrication complexity. And for the gluing between the whole assembly panels, we choose the JB Weld acrylic epinox. This is a kind of water resistant glue and also can make sure it can generate enough force to assemble these panels together. Also, it is biocompatible, will not cause any toxic stuff to the zebrafish sample. Then for the imaging chamber mounts, we design these mounts to make sure customers can easily remove the imaging chamber out and reinstall it into the onto the optical table, because customer may need to routinely clean it and also add water or move water out. So this is why we designed these 4 external mounting system. And the imaging chamber mounts should be as cheap as possible and also has the low fabrication complexity. So we choose, besides, the imaging chamber mounts do not need to be transparent since it will not block too much light from the bottom panel. Then we choose the 2011 alumni as the material for the imaging chamber mounts based on its high reliability and ease of manufacturing. So to make sure it will not block too much light from the bottom panel of the imaging chamber, we make sure the imaging chamber mounts dimensions are as small as possible, which are 12.7 millimeter times 25 millimeters height. So we then minimize their vertical surface area, which is the surface that touch with the bottom panel of the imaging chamber. And also it will need to be strong enough to support the weight of the imaging chamber when the imaging chamber body gets full of water. For the material selection for the imaging chamber body and the optical window, we need to find the balance between the transparency and the price. So based on this price and transparency chart, we because we only want to keep the transparency as high as possible, we only choose the top 5 transparent material in the water clear level, which are silica glass, PC glass, and Pyrex, and PMMA, and the PET glass. The PET plastic. So to quantify the transparency and the cost, we we create a ratio that between the transparency and the price. We call it the transparency price ratio. This ratio can be calculated based on this equation below. The transparency can be represented by the maximum light transmission in percentage unit, which is the second column of this table. And the price can be represented as price per cubic inch for each kind of material. And this kind of information has also been shown in the third column on the right-hand side. So we calculate all of these top 5 transparent materials, transparency to price ratio. We get the Pyrex as 163.6 TP ratio, and we got the PMMA, which is acrylic board we are using, is 173.6 TP ratio. So that's why we choose the acrylic board, the acrylic as our final material for the imaging chamber body and the optical window.
To prove our imaging chamber can be operated under extreme condition, we did hydrostatic analysis to our imaging chamber based on the hydro pressure law. when it has a extreme condition, which is water density is 1,000 kilogram per cube meter, and the gravitational acceleration is 9.8 meter per second square, and the height of the imaging chamber is 33 millimeter. Under this extreme condition, the pressure under the imaging chamber is 302.23.73 Pascal. And we will use the JB Weld acrylic epoxy to combine the panels together. The JB Weld acrylic epoxy can provide 3,900 PSI bending strength, which is much higher than the required strength. So the imaging chamber will be perfectly operated under the required condition. To make sure the imaging chamber can be stable on the experiment table, we did the chamber stability test. The weight of the chamber will be distributed among 4 supports. So in this way, the four supports will be placed symmetry. In this way, the center of the mass will be exactly at the center of the imaging chamber. So the imaging chamber will not be tipped over. It will be stable on the experimental table. In our imaging chamber design, we use for 2011 alumni alloy supports. We did static analysis to these supports. Under the operational condition, each of the supports will under 0.55 Newton force, which will cause 4,342 Pascal pressure. Our mounts will be made from 2011 aluminum alloy, whose strength is 379 megapascal, which is much greater than the required strength. So these mounts will be strong enough to support our imaging chamber and make the imaging chamber stable on the experiment table.
All right, we'll now transition to our fish holder subsystem. The purpose of this subsystem is to effectively hold the zebrafish sample in place while also being able to move vertically throughout the imaging chamber. As you can see, this subassembly is made from 2 unique parts. We have the mounting base, which is attached to a vertical translator, and the functional surface, which the laser may pass through and analyze the specimen. The mounted base is made from 3D printed PETG material, which can maintain structural rigidity given the load of only a few grams. Along with the low cost, the PETG material can also remain intact through long exposure to water due to its water-resistant characteristics. In accordance with Customer Need 10, the geometry of the mount makes the part relatively easy to manufacture, and it allows for simple vertical translation in the imaging chamber due to its mounting on the single-axis translational stage from Thorlabs. The functional surface is a clear PMMA acrylic material. This was chosen to satisfy Customer Need 8, which requires the holder to be transparent enough for the laser to not be disrupted. It is also structurally sound enough to sufficiently hold out given the loading while also being water resistant. Since we are using PMMA, this poses little to no threat to either the specimen or personnel working on the subject. This satisfies the 18th customer need. Based on the sizing given from the 7th customer need, the functional surface will be 12.7 millimeters wide and 38.1 millimeters long. This provides ample room for most zebrafish specimen to be tested. We chose to use an acrylic epoxy to mount the functional surface onto the fish holder mount, since fasteners would likely get in the way of the laser and would possibly be over-designing the entire assembly. The acrylic epoxy, like all other parts of the fish holder, are water resistant and can uphold the weight of the zebrafish samples. This satisfies customer need 14 and 15, with the holder not causing any harm to the specimens while holding against an appropriate water level.
So our next slide is going over the specific fish holder dimensions, which are shown better in the diagram on the right side. So as we discussed, the actual fish holding functional surface is 12.7 millimeters wide by 38.1 millimeters long and has a thickness of 3 millimeters. And the actual main body of the fish holder itself is 57.15 millimeters long, 50.8 millimeters tall, and also has a width of 28.58 millimeters at its widest point. And one specific part we wanted to make sure we included was the actual gap in between the front of the fish holder and back of the fish holder. And this allows for the fish holder to be easily moved in and out of the imaging chamber without actually impacting the imaging chamber itself. So it fits within the working space. And then our first analysis is a force analysis, because a shear will be generated on the epoxy holding the functional surface to the main body of the fish holder. We performed this force analysis where we found that the total weight of the agarose gel and the zebrafish specimen itself would be 6.867 newtons. So we did the shear analysis as shown here and found that it would generate a shear force of a shear pressure of 0.18 megapascals. And based on manufacturer specifications for the epoxy that we'll be using, it can handle up to 26.78 megapascals. So our load is less than 1% of the actual max stress that the epoxy can handle. And then for our mounting, we'll be using two 1/4 by 20 screws because that's what the Thorlabs LT1 requires for any external mounting, as can be shown by the hole dimensions here. And then we also performed a static analysis to make sure it wouldn't deform on its own once it is actually mounted. So we modeled the fish holder in SolidWorks and found that it has a mass of 31.8 grams or 0.312 newtons, and then did basic force balancing to find these. And so we found that the G value, which is the weight of the fish holder, is 0.312 newtons, which is also the same as the reactionary force in the Y direction as shown by the orange vertical arrow. And then by doing a moment analysis, we found that the reaction force from the actual fish holder pressing against the Thorlabs LT1 was 0.35 newtons. And then by balancing it with the first equation, we found that Fs, which would be generated by both of the holes, since we would have two fasteners, would each be 0.175 newtons.
So this is our optogenetic laser paths, and you can see some of the components here. The customer required us to have a mechanism for switching between the optogenetic laser path, which we designed, that includes the 48 nanometer laser. And the 48 nanometer laser must be switchable between our path and an already existing customer path that includes a 639 nanometer laser. The laser path was also required to be assembled by lab technicians using standard tools. And also, the customer required that the assembly be accessible to 95% of males and females. And given the dimensions of our laser path, we satisfied these requirements. The laser path was also required to be aligned well so that the laser path travels through it efficiently. and accurately without any aberration or distortion. Here is an exploded view of our laser path so that you can see some of the components. Here is a representation of the layout of our laser path. We start with a 488 nanometer laser and heatsink. The laser passes through a shutter and OD wheel. And here you can see our switchable mechanism, our M1 mounted on our magnetic base. For our laser path, this M1 would be moved out of the way because the magnetic base is removable. There are two top edges that are removable, and the mirror one would just be moved out of the way for our laser path. But because the customer requires that the 488 nanometer laser also pass through a calcium imaging path, that mirror will redirect it towards that path. But for our path, again, our optogenetic stimulation path, it would actually not be in the way, but it is just shown here to show where it would be. And after the laser path travels through that, doesn't actually hit it, goes to our L1, our first beam expansion. The customer required that the diameter of the laser be expanded from 0.8 millimeters, which it starts out as, to 27 millimeters. And we achieved this using two beam expansions, the first of which is shown here with the L1 lens and the L2 lens. After coming out of that beam expansion, the laser hits a mirror M2, which will redirect the laser to a periscope. And this is a top view. This is a top view of our laser path. And here in these section cutouts, you can see right views. And this is a right view of the periscope. The laser will hit M3, which will redirect it upwards. The laser M3 is about 45 degrees from the horizontal axis. And this M3 mirror will be mounted in the periscope. After that, it is redirected upwards to hit M4, which is also mounted on the periscope, which redirects it then to a DMD. Now, the DMD is basically a series of small mirrors, which will allow certain sections of light to be reflected and not allow certain sections of light to not be reflected. And this will create a pattern. This is the river pattern that the customer requires for stimulation of the zebrafish to study its effects. And after coming out of the DMD, it reflects and hits mirror M5. Now we go to our second beam expansion, which is consists of lens 3 and lens 4. At this point, the diameter of the laser is 8 millimeters. After this expansion, it is now 27 millimeters. It then goes and hits mirror 6, passes through the tube lens, hits a dichoric, which that dichoric is attuned for our 488 nanometer wavelength, and it will interact with our laser and redirect it to M7. The dichoric is necessary because the customer will place a camera behind it to get light from the zebrafish from the calcium imaging path. And that light will come from the imaging objective up to the mirror 7, pass through the dichoric because it allows that wavelength of light to pass through it. And behind the dichoric will be a camera, which will capture the map of the brain of the zebrafish. But because our laser path is a wavelength of 488 nanometers, it will actually reflect off the dichoric and reflect to M7. This is a top view of M7, and you can see at the bottom there's a right view. And you can see that mirror 7 reflects the light down to the imaging objective and down to where the zebrafish will be. And it will project the optogenetic stimulation, the pattern of the river, the simulated pattern of the river. So yeah, that is our light path. And here you can see the components of our light path, the off-the-shelf components. And you can see them in reference to the figure past that we just went through. And if you'll note here, lens 1, lens 3, the part number AC 254-030. 30 is the focal length of the lens. It is 30 millimeters. And also listed is the focal lengths for the other components of the lenses for the beam expansions. You can see 300 and so forth, 100 and 300 for the other lenses. So in our laser path, the mirrors are aligned so that the incident angle of the laser coming in to the mirror is 45 degrees. And by the law of reflection, the incident angle must equal the outgoing angle. So because of that, we will redirect our laser 90 degrees. Also important is the positioning of our lenses. They are positioned from each other so that their focal lengths, so that the distance between them is the sum of their focal lengths. Now here is the beam expansion, and we can use the focal lengths to determine the actual expansion that is achieved by the beams and by the beam expansions using their focal lengths. And some of the calculations are here. You can see for the first expansion, we have the layout of lens 1 and lens 2 being 300, and you can see their focal lengths are divided to find the magnification, which would be how much they expand the beam. And you can see that the incoming diameter is 0.8 millimeters, and multiplied by the magnification, the outcoming diameter of the laser beam would be 8 millimeters. And the same is done for expansion 2.
Great, thank you, Brian. So now let's recap some of the design characteristics and key features of our design. So our major objective of this concept is to have, as Rachel mentioned, great user accessibility. So we designed a simple mounting mechanism that allows for easier movability of the fish chamber, which allows for cleaning and sanitizing and running multiple experiments. The acrylic fish chamber remains clear and relatively easy to clean with non-abrasive cleaner. The spacious laser path setup allows for parts to be easily removed or replaced, meaning it's very accessible and won't cause any major obstructions when trying to modify any of the laser path parts. And the multi-material fish holder allows for clear view of zebrafish, which was the PMMA, with low manufacturing costs, which would be the 3D printing of PETG. Now, talking about costs, here's our cost table summary. For the prototype, our total cost was $75.57. Off-the-shelf parts, including all the mounting fasteners, it was $1.20. The raw material, including aluminum, the aluminum tubing, including aluminum tubing, aluminum steel rod, the acrylic sheets, both 1 millimeter, the epoxy glue, and the PETG filament costs about $4.72 per part. The assembly costs $42.56, including the assembly of all the gluing of all the panels and gluing the fish holder together. And the manufacturing is 4 cents per part, and the energy is 5 cents per part. The shipping and tax was calculated to be $27. So our total is $75.57 for the prototype, which is less than the $300 budget that we had as stated in our customer needs. Now for the 100 unit production run, we saved quite a bit of money because we bought in bulk. So the off-the-shelf materials, we went from $1.20 to 86 cents, and the raw material, including aluminum rod, acrylic sheeting, both 3 millimeter and 1 millimeter, glue and PETG filament, is $2.61. The assembly is the same because we measured assembly as assembly time, so it costs the same amount of money to assemble one. And the manufacturing and energy costs are the same for one of them. The shipping and tax was a big savings for us, because the shipping and tax was estimated to be around $67 for all the bulk parts, and we divided that into 100 of the units so that each unit costs about $67 cents in shipping and tax. So here's a cost table summary of the prototype. Here we can see the part assembly name, the description, its quantity, its production or vendor, the cost per part, or the total cost. So for the prototype, the fish holder was 3D printed and glued using PETG and the epoxy we mentioned, and it cost $23.65 to make one fish holder. The imaging chamber was produced by cutting the panels, the 3 millimeter and 1 millimeter panels, and gluing them with epoxy, and it cost $39.10. The corner bracket mounts were machined from the aluminum rods, and it cost $2.91. And to produce 4 of them, it's $11.64. Fish chamber mounting screws and fish holder mounting screws are 11 cents and 37 cents each, totaling our cost of $75.57. All these costs in this summary prototype include shipping costs and include shipping, manufacturing, energy, assembly time, and raw material costs. And the same applies for this production run of 100 units. Here's a cost table summary for that. So the fish holder costs $22.95 to produce 1 of them. So 100 of them is $22.95. 100 imaging chambers, they cost $19.81 per, so $1,981. The corner bracket mounts, 400 of them because we need 4 per assembly, 71 cents each. It costs $284 for all of them. Similar situation with the fish chamber mounting screws and the holder mounting screws, about $44 and $74 for the cost of those fasteners, which is, as we mentioned here, this cost is way below the $200 that was required in the customer needs for the production run. So why choose Poseidon? Well, our imaging chamber is very low cost and we have a short manufacturing time, and we are really focused on having an ease of like really high accessibility for the end user. So it's very easy to assemble and very easy to clean, sanitize, and maintain. Our fish holder is very low cost, and since we're using PMMA as the fish mounting surface, it has great adhesiveness and the fish won't really slip out when the gel is applied. It's really easily cleaned as well. Our laser path has a short assembly time and it's very accessible to modify any of the parts or swap them out.
So in conclusion, Poseidon satisfies the customer needs while maximizing profit and minimizing manufacturing. It's focused on user accessibility. Poseidon is easy to maintain, assemble, and sterilize. Poseidon is designed for laboratory use and is BSL-1 level compliant. Our product meets a very specialized need that no other product in the market meets. And it does this while providing the user with a key feature of a removable imaging chamber that allows for easy cleaning and maintenance. So these are the key features of our product. And thank you for attending our presentation. And now we are able and willing to answer any questions you may have.
Hey guys, this is Tom Singer from Northrop Grumman. Good job on the presentation. I liked it. One thing that you commented on early was that you have like a requirement for like optical transparency. I don't know that I saw, and I looked at the customer needs statement months ago, and well, probably a month ago, and I don't recall. Was there a specific need for some level of transparency in that?
Yes, there was no specific number for the level of transparency, but it did need to allow a laser to pass through the walls of the imaging chamber and for light to pass through the surface that the fish was going to be held on. So we decided in the effort to make the design as functional as possible, to emphasize the transparency of our imaging chamber and fish holder. Okay,
because I know you had a slide where you're doing like a trade study and looking at transparency versus price, and I'll maybe talk a little bit more about that in a moment. But when you're talking about, oh, this material is 97% transparent, this material is 93% transparent, is that I don't see any. I would think that would be somewhat dependent on thickness, and I don't see any sort of accounting for the thickness there, and also I don't see, again, what a customer requirement is, right? So if the customer says, hey, this has to be, has to be able to shine a laser through it, the first thing that I would want to do is go ask the customer, can you define that requirement a little bit more clearly? And I was talking offline with Dr. Traum, and I know he said the customer was maybe not the most communicative with you guys, but I think that's maybe an important thing to figure out, especially in the context of a trade study like this. So I'll say that I do appreciate you doing a trade study and thinking about, what different materials can we use and how can we evaluate those. I don't know that transparency per price is really, especially price per cubic inch, is really the right measure here, because I don't think that you're buying any of these materials in bulk in the sense that you would measure them in price per cubic inch. And a lot of the actual volume of material that you're going to need, again, is going to come down to, what can you easily get? What sort of strength requirements do you have? Things like that. So, and the other side of that is when you present your overall cost summary, and 95% of your cost is in the assembly labor versus 5% of your cost in the materials. Ranking things on price when it's such a small component of your overall cost just doesn't seem like it's going to be that big a driver for a trade study. So something here that maybe might have made more sense is, are any of these materials maybe driving ease or complexity of manufacture or assembly would maybe be a better metric here. But I do like that you're considering trade studies and kind of showing that. I'm a structures guy, so I'm going to pick on your structural analysis. You were doing bond strength twice, and I do composites, and so I'm sort of in the world of bonds, and these jumped right out at me. You had two analyses of your bond. One was here, and you're talking about, okay, we've got the hydrostatic analysis, and we say that we're creating rho GH, right? So 323 pascals of pressure on the face of this sheet, right? And then you're saying, oh, well, our epoxy can hold, 3,900 psi, or to 26 million pascals. We'll keep the units the same. I think if you think about it for a little bit, you'll realize that you're not so worried about the comparison between the pressure acting on the overall surface of your window and the pressure that the bond, or the strength the bond can hold, right? Those are sort of two different things. Your bond is effectively holding the integral of that pressure over a much smaller area than that pressure, right? So I don't think that's the right calculation to be using there. The other thing I'll say is, and I said this with the other team, and Dr. Traum sort of mentioned that he was encouraging you guys to think about fluids because he's a fluids guy. But filling a chamber like this with 3 inches or so of water just doesn't seem like a major structural load. To me, the bigger thing is going to be handling loads, right? So if somebody's picking this up, how are they holding it? How is, are they moving it? Are they bumping it? Those sorts of things. Those are going to be the more critical structure things. And then the other bond thing I'll pick on the fish holder, right? So you've got right here. You're showing that this bond is reacting shear. But if you free body diagram the little support out on the end here, I think you'll find that shear is not the only force that you need to react there. Right, so bonds tend to be great in shear. They tend to be not so great in tension. I don't think it's a concern, right? I certainly wouldn't expect anything. I mean, to me, structural analysis, and again, I'm a structures guy, and I like to see it, and I appreciate it. But like structural analysis on just about anything in here, it seems like it's being done just to check a box because there's nothing here that really jumps out at me as a significant structures concern with, the scale of the parts and the loads that are being put on them. But if you're going to do them, definitely consider that moment going in there. One other thing I'll mention is I think you showed like hex bolts holding this fish holder to the vertical translation deal. Yeah, how accessible are those bolts? Like if somebody has to get in and attach them, are they going to be able to do that with a wrench, or is there maybe a different fastener that you could spec there?
So it would be possible to use quarter 20 screws instead of those that could be more accessible. I think given the orientation and with the space limitations from the top edge of the fish holder, the hex bolts would likely be the most accessible, just for ease of hand tightness.
I'm looking at that chamfer that you've got in there. I like that you have a chamfer because again, structures guy, I don't like to see sharp corners, and I kind of suspect you might have one over on the other side. But you've got a chamfer here, and I appreciate that. But I think you might wind up having a clash between the chamfer and the head of the bolt, or at least maybe difficulty accessing with a tool.
Okay.
What we could do instead is replace those hex head bolts with like a rounded screw head, and so it could be accessible from like an Allen wrench. So it's a small tool that can kind of fit in
kind of what I
there.
was thinking might be a better choice there. And I also like that you have grade 8 bolts, down there, which is massive overkill. But your CAD model is very detailed.
Thank you, sir. I appreciate the feedback.
Hey guys, this is Arvind from Cummins. I have a question about the chamber panel. Not sure if I missed this, or did you ever explain how? I think at the beginning you mentioned that this is an add-on kit, but I didn't see how those, and then you showed an exploded view here. How are they connected with each other? Is it just epoxy glue?
Yeah, they are glued by the glue we mentioned. They just
Okay.
directly glued together.
Okay, I guess that's why it was in the other calculation slide. So just wanted to confirm. And then how are they sitting on top of these chamber mounts? Are they just fitted, press
Yeah.
fit?
Yeah, that's what we want, because that will let the imaging chamber can be taken off easily and reinstall on the optical tool much easier, because for customers, they need to clean it routinely and actually each time after and before experiments. And they need to change the water and pour it out and take some new water inside. So we don't want let it to be too complicated, like screw it in and screw it out every time. So we just let it to sit on it.
Yep, like Thomas mentioned, just handling it. Have you thought about the use case? Is that really feasible? So something to just think about that. Another question I had was about the 3D printed part. If I'm not mistaken, and I'm going to start annotating here. Oh, never mind, you moved. Okay. That's
Sorry.
good. Good. So I'm guessing this part here is also 3D printed, right?
Yes.
So you're going to submerge, so I'm gonna delete that, this part and this part into the water. Have you thought about the allowable material used repeatedly in a chamber that you put, some sort of fish in there, right? Is that going to be an allowable material? Or even if it is, 3D printing is cheap, yes. Feasible, it it's pretty strong for most cases, but there is a chance of growth of undesirable material on it over time. Have you guys thought about that?
Right. So one of the ways we designed this was we had three materials in mind. We had PLA, ABS, and PETG. Out of all of those, PETG had the lowest cost and one of the greatest water resistance. If we were to use PLA, it would just dissolve over time. But PETG is relatively water resistant, and if we show during some sort of testing of prototypes that there is an issue with repeated water like submersion, we would likely spray it with some sort of sealant in the area to prevent that from becoming an issue.
Okay, just something to think about. I think overall you guys did a good job explaining your design. You broke it down very well into the subsystems, and you all did a good job explaining all the functionality. I think overall in your presentation, sometimes it would be good for an audience such as ours to say the looking at the customer needs, it's a long list of things, and overall it's a good practice to say, I think I'm talking about one of your slides that you calculated a bunch of numbers. Yes, great to see. And you said we are 1% of the overall load that we would need. Just having that kind of as a side note or a bottom saying, this is the requirement, we pass it. Just doing the calculation might not give the overall explanation that's needed for an audience to understand, okay, you did your calculation, but did you pass or did you fail? And I think you said it verbally, right? Just a good practice overall to, if you're passing, take the credit, note that and document that there as a side note. I think last question I had was in your cost. I think you had a table that said energy or something like that. It's a little bit open-ended, but that's fine. And okay, 46.78. All right, because I saw, I was writing down some notes and I saw 4,600 something, and I was kind of shocked. But okay, I see the decimal there. Other than that, I think you guys did a good job of presenting your material and putting together slides. But yeah, congrats.
Thank you. Thank you very much.
While we're looking at this slide, and again, assembly is the huge driver of your cost. What other sorts of systems did you consider that might have driven that down?
So originally, we decided to try to do some injection molding that might help reduce the assembly cost significantly, because these both assembly costs are based on manually assembling each.
Yeah, and is that, can I ask, because I know you kind of had the laser, the optical path as sort of a separate requirement, and again, I was talking offline with Dr. Traum, he said that sort of got deleted from some of the team's projects. Is your assembly cost just for the box and the fish holder?
Yes, because we assume that the customer will assemble their laser path with their components wherever they wanted to research. Yeah.
Okay, so injection molding, I didn't mean to interrupt. I just want to clarify that one point. But so you were saying you were thinking about injection molding?
Right. We were thinking about injection molding for the production run. And it would be significantly cheaper, like an upfront cost of $100 for the mold and then $4 per part or something like that for the entire assembly. But we didn't think it warranted going that far for an injection molding, since we're only producing 100 units. If our production volume was greater, we would have definitely moved to injection molding, but we were only assuming 100 units. And since it's such small scale, it did not seem necessary to spend that much on a injection mold.
Yeah. Did you say $100 to make a mold and then $4 unit cost?
Something like that, yeah.
Yeah. So now you're talking about if you're making 100 of these, you're talking about like a $500 cost for your production run, which is going to eliminate I would guess the vast majority of your assembly cost versus a $4,000 run of 100, right? I mean that's a not insignificant reduction in price, and if a customer is willing to pay $50 for these, and if you sell them 100 for $5,000 and make $4,500 worth of profit versus $400 profit, that's maybe something significant.
Definitely, yeah. Our assumption of $100 is very rough for the mold. There's definitely other costs associated with it that we try to estimate, and from the top of my head, I can't remember exactly what the costs were, but just the mold itself was about $100. But there's
Okay.
another upfront cost that I don't remember right now.
But yeah, I mean, that does seem like, an almost ideal application for something like injection molding, other than, maybe your production run is a little bit low to justify that. But otherwise, I mean, it's perfectly suited for something like that.
Right. Another issue that we had with the production of injection molding was also the geometry of some of our parts. For example, the fish holder. We had a discussion with Dr. Trom, and he mentioned that doing an injection mold for this would be relatively difficult. So that would definitely drive the cost a little higher. Especially because of this like sharp edges on the corners and the holes, I think he mentioned.
Do you need
So-
sharp edges?
Not necessarily, but we would
I mean,
have
if
to.
anything, sharp edges are working against you.
True. But I think we should definitely, we would definitely have to do a small redesign if we wanted to go for injection molding.
Yeah, I would say even at a scale of 100, 3D printing is questionably beneficial.
Right. We could just print 50 parts at a time and be done with the entire thing.
Okay, any more comments or questions from our panelists? Nope. Okay, well, seeing no more comments or questions, I think we'll wrap it up there. So I want to thank you guys for sharing your design with us, and thanks for being flexible on the start time. Sorry to jar you guys in your your final presentation by starting things late, but you handled it flawlessly. So thanks for making me look good, as you guys always do. I think with that, we'll wrap things up for the panelists. We've got it's about a 20-minute break now built into the schedule. We're meant to reconvene it at 1:15 p.m. Let me just for completeness drop into chat the next link. See if I can find my chat. There it is. Too many windows. There it is. Okay. So the next link is coming through in chat, and we'll reconvene there at 1:15, and hopefully that'll be the first presentation that I managed to start on time today. But until then, we'll wrap it up now and leave you guys the room if you want to debrief or decompress. Good job, and thanks again for all your hard work this semester.
Just
Thank
also
you.
wanted to thank the panelists again for coming. A lot of great feedback. Thank you.
Yeah, thank you very much.
Thank you very much.
Thank you.
Welcome.
Thanks, guys.
Thanks,
Go
everyone.
Gators.
Very good. Okay. Thanks, guys. We'll see you.
See you, Dr. Trump.
Yeah, see you.